Hello, good afternoon.
Afternoon, Doctor.
Good afternoon, Doctor.
Hi, Doctor.
Okay, here, please share the screen. Have you watched the video, the lecture?
Yes, Doctor.
Yes, Doctor.
Yes or no?
Yes,
Huh?
Doctor. Yes.
Yes, okay, so we can discuss today. I will present today's lecture in the form of tutorial with question and answers so that to help you to understand the chapter better with question and then with answer. Nampak?
Nampak, Doctor.
Can you see the slide? Okay, good. Okay, good afternoon. Okay, next lecture will take about 1 to 2 hours to complete. And then we are going to have another lecture next week regarding how to find a novel gene. Where at the end you have to submit assignment in group in about 2 to 3 weeks on the topic how to find a novel gene. Next week I will explain about how to find the novel gene using BLAST. Okay, for today's tutorial, okay, discuss on conservation of DNA, protein, and structure. Which one do you think that is more conserved?
Protein structure.
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 Okay, can you see the screen now? Okay, can I? Okay, discuss on conservation of DNA, protein,
Yes,
and
sir.
structure. Which one do you think that is more conserved?
Structure.
Structure.
Structure. And then which one ranks second after the structure?
Protein.
Protein and then DNA. Why? Why protein? Why structure is more conserved than protein, and then protein is more conserved than DNA? You can relate this question to the codons that code for the amino acid. How many codons available today?
64 codon.
Okay, 64 codons code for how many amino acids?
20.
20 amino acids. Okay. See, this is the codons. The code for 20 amino acids. Some of the amino acids, they may have more than one codons. For example, valine here, the 4 different codons code for the same amino acids. Right? DNA is less conserved than proteins, and then protein is less conserved than the structure. And then as there are 64 codons, and then 3 of them code for stop codons, which is TAA, TGA, and TAG. So the remaining is 61 codon code for 20 amino acids. Okay. For example, mutation at the 3rd position of GCT, GCU, GCC, GCA, and GCG, they still code for the same amino acid, which is alanine. Right. So in some cases, changing at the 3rd of the nucleotide of the codon may not change the amino acids. So this is because of degeneracy of genetic code. That's because of degeneracy of genetic code, DNA is less conserved than proteins. Because in some cases, different codons, they will code for the same amino acids. And then the 20 amino acids can be grouped into different groups according to their side chain. For example, non-polar amino acids, which are either aliphatic or aromatic. And then polar amino acids, which can group into polar, uncharged, polar, positive charged, and polar, negative charged amino acids. And for example, acidic amino acid, basic amino acid. Right. And then, therefore, the structure is more conserved than protein because of conservation substitution. In some cases, substituting from amino acid from the same group, for example, basic amino acid, substituting from basic amino acid consists of histidine, lysine, and arginine. So substituting from lysine to arginine is most of the time may not change the structure because they group under the same group of the amino acids. We call this as conservative substitution. Because of conservative substitution, and then the protein structure is more conserved than protein sequence. And because of degeneracy of genetic code, protein sequence is more conserved than DNA sequence. So there are 2 points here for this slide. And then if you like to get the full marks for this kind of question, make sure you have 2 points. Right? Okay. First, structure is more conserved than protein. Protein is more conserved than DNA. And then second, because of degeneracy of genetic code, and then the protein sequence is more conserved than DNA sequence. Because of conservative substitution, a protein structure is more conserved than protein sequence. So it's very simple. Eh? Relate homologous residues in sequence and the structure. Who can answer this question? When we align a few 2 or 3 sequences using pairwise sequence, constructing pairwise sequence alignments or multiple sequence alignments, you will see in some column the amino acids are identical. Why they are identical? Because they are, if you perform multiple sequence alignment, you see for certain column, the amino acids ratios totally identical for all the protein sequence that you align. Why? Do you know why?
They are conserved
Huh? What?
because they are conserved region.
Yeah, they are conserved, and another things we can say is they are homologous, right? So as you can see here, this is the multiple sequence alignment for protein sequence 1, 2, and 3. At certain column, you see the amino acids are identical. They align, the same amino acid align at the same column for the C, CP, and VAR, S, and then F, N, V, C, K, right? So a multiple sequence element is a collection of three, not two, three or more protein sequences that are partially or completely aligned, right? This part completely aligned, and then the other part partially aligned. So you see, this is the picture that you can see from multiple sequence alignments. And then when the aligned column, the analyses are identical, meaning that they are homologous residues. These homologous residues, they are aligned in the column across the length of the sequences. So across the length of these sequences, some of the amino acids, some of the column, the amino acids are identical for all of the protein sequences, meaning that these are the homologous amino acid residues. And then the asterisk hit all the asterisk column representing homologous amino acid residues, right? Okay, these aligned residues are homologous in an evolutionary sense. Why? Because evolutionary sense, right? Because they are derived from a common ancestor, right? So if the aligned amino acids are identical for all of these acids, and then they are related evolutionary, right? And then meaning that these amino acids are homologous, they're conserved, and then they are derived from a common ancestor, right? And then some of the residues in the column, for example, for this one, right, presumed to be homologous in structural sense. This because for this of the homologous amino acid not only align at the sequence level, but they also align at structural level. For example, VAR here, valine, alanine, arginine, they align at the sequence level here, and then they also align at the structural level here. These few amino acids representing valine, alanine, and arginine, right? So the homologous residues, they are homologous. They can be homologous in the sense of evolutionary, or in the sense of at the structural context, and also at the sequence context. There are two things. How do you assess the accuracy of multiple sequence alignments for divergent sequences? Meaning divergent sequences means that sequences with low identity, right? How do you assess sequences with low identity? For sequences with high identity, whatever program that you use to align them, most of the time you will get almost similar multiple sequence alignments, regardless which of the approach that you use to align a high identity protein sequences, right? Because it's not challenging. Either use progressive alignment, iterative approach, consistency-based approach, structure-based approach, you will get the same or almost similar multiple sequence alignments for high identity protein sequences, right? But if you would like to align low identity protein sequences, this is a very challenging task, right? Okay. Huh? Anything? Someone is talking or asking question or what? Just now. No? So the multiple sequence alignments for sequences with high identity, right, are normally similar, regardless which approach you use to do the alignments. But for multiple sequence alignments for low identity sequences are difficult. Because for low identity sequences, you will see a lot of different throughout the sequences. In some cases, you may see a lot of insertion and deletions, right? And then protein structures evolve over time, and then protein sequences evolve more rapidly than the protein sequences. For example, two of the well-known proteins that you learn from for example of the lecture throughout the bioinformatics course, human beta globin and myoglobin. Right, this is hemoglobin, and then this is myoglobin. Right, these two, you see the structure for subunit of the hemoglobin and also the myoglobin are almost the same, almost identical. Right, you just twist this one, you twist, and then you see, in fact, the structures are almost identical, despite the sequences shared between myoglobin and beta subunit of hemoglobin just about 25 to 27% identity, very low in terms of the sequence identity, but the structure are highly similar, right? So in creating a multiple sequence alignment, it may be impossible to identify the amino acid residues that should be aligned with each other or as defined by the 3D structure of protein in the family. Right? Therefore, structure and functional data are needed to access the alignments. When dealing with low identity protein sequences, when you do the alignments, you need structural information to guide the alignments. You need structural information to improve the quality or to improve the accuracy of the alignments. Okay, some of the programs that make use of secondary structure and functional residues. Some protein they make use of secondary structure to guide the alignments. Some of some of the programs they make use of tertiary structure to guide the alignments. When you align low identity proteins, since the numbers of aligned column with the homologous residues throughout the sequences are very, very few. And in that cases, you may not know whether you obtain accurate alignment or not. So in order to check, you can check the structural information. For example, active site, metal binding site. This type of the structure, this type of the functional residues should be aligned at the same column. Right. You can also check the arrangement of the secondary structure throughout the alignments. For example, alpha helix, beta sheet, they should align at the same column throughout the alignment. This is how you check on the accuracy of alignments based on structural information. This is secondary structure and also the functional residues. How sensitive the multiple sequence alignments in detecting distant homolog over pairwise sequence alignments, right? Why we use a multiple sequence alignment to detect distant homolog and not use just using the pairwise sequence alignment to detect distant homolog. So when you detect two sequences, it's very hard for you to identify or to determine which of the amino acids are homologous, which of the acids are conserved, right? Because they're just representing two of the protein sequences. If you like to get more information, you have to align more sequences, which is performing multiple sequence alignments. When aligning two protein sequences, the pairwise sequence alignment is either highly similar for the two sequences that share identity, or highly dissimilar for two sequences that share low identity. Right? So hard for you to figure out, to identify which part of the alignment, which part of the alignments are conserved, which part of the elements are not conserved. It's very hard to identify. So this alignment ambiguity for divergent sequences hamper the detection of distant homologs. Hard for you to tell whether they are distant homologs. And then multiple sequence alignments, for example, for this one, right, is more sensitive than pairwise sequence alignment to detect distant homolog, where you can see the conserved region, right, could be easily seen and identified from multiple sequence elements. If you align only two sequences, you may not know, okay, this is what domain, and this is what domain, and then this part is highly conserved, right? And then this part also conserved. Because you may not sure, you're not sure on which part of the alignment is conserved, which part of the alignment is not conserved. In order to have a bigger picture, a more accurate identification on the conserved region, you have to align multiple sequences using multiple sequence alignments, right? Okay, list 5 approach to multiple sequence alignments. Can you tell me 5 of the method that is discussed in the lecture note? Method number 1 is
Exact method.
method.
exact method. Second,
Progressive
Progressive
alignment.
alignment.
progressive alignment. And then third,
Iterative approach.
approaches.
iterative. Okay, and then the fourth,
Consistency-based methods.
consistency-based method. And then number 5,
Structure-based.
structure-based method. Okay, and then there are 5 approach to multiple sequence alignments. And then the program offer trade-off in terms of the speed and accuracy. If you like to have better accuracy, maybe you have to compromise a bit the speed. If you like to have a better speed, maybe you have to compromise a bit in terms of the accuracy. So, but normally most of the program, they will take a balance between the speed and also the accuracy. Right? These are the 5 approach to multiple sequence alignment. Exact method, progressive alignment, for example, cluster W is very well known. And then even though it's not a very accurate, but the platform is very easy to use, and then it's very popular. And then the iterative approach for the praline, interalign, master, Maffei. Okay, master is very well known. Yeah, it's very fast, and it can align many of the sequences in a very short time. And then consistency-based approach, for example, ProcCon, Tcoffe, the well-known one is Tcoffe. Right? And then as structure-based method, espresso. This is the method that use structured information to guide the alignment. So this of the 5 approach, they had a trade-off in the speed and accuracy. If you would like to have better speed, maybe you have to compromise a bit the accuracy. If you like to have a better accuracy, you have to compromise a bit the speed. What are the pros and cons for exact method? In chapter 2 or chapter 3, you learn how to perform global and local alignments, right?
Yes, Doctor.
Ingat tak? Yeah, by constructing the matrix, right?
Yes.
In 2 dimension, dimension X one sequence, and then dimension Y the other sequence, and then you have to compute every single cell in the matrix in order to identify the alignment using what procedure? Trackback procedures, right? Right? In order to identify the local and global alignments. Okay.
Yes,
In
Doctor.
fact, this is the example of the exact method. Right? So, do you think it's easy to get the alignment for sequences if the sequence is very long? Maybe it's very difficult for you to do so, right? Because you have to fill up all the cell in the matrices in order to get the alignment. So it's very time consuming. Right? And then this exact method is only feasible for a short amino acid sequences in just and involve just a few sequences. In that case, it's still possible. Right? If the sequences of the proteins that you are going to align is very long and involve many of the protein sequences, it will take a very long time to compute the every single cell in the matrices in order for you to identify the best alignment or optimal alignment based on the matrices that you constructed. Right. So this exact method, they employ dynamic programming for alignments. You have learned in chapter 2, dynamic programming. The exact method, they use dynamic programming. Do you know what is dynamic programming? Who can answer this question? Dynamic programming. Siapa boleh jawab dynamic programming?
Break down into different word size.
Huh?
Is it breaking down into different word size?
From different website.
Word size.
No programming, not the website. You see this? This is a matrix used to compute the global alignments. Right. So if you like to align 2 sequences, sequence 1 and sequence 2, right? Since involve 2 sequence, the matrix that you have to solve is in 2 dimensions. One is for sequence 1, the other one is for sequence 2, and then you have to fill in every single detail here, right? Right. And then you can assume that to get the final alignment, pairwise sequence alignment, is a complex problem that you are going to solve. So your ultimate aim is to solve the complex problem. But in order to solve the complex problems here, you have to divide the complex problem into many of the sub or small problems. For example, one single cell here representing one sub problem, this another sub, this another sub. So in order to solve the complex problems, you divide the complex problems into many of the sub problems. This is a simpler, right? We call this as dynamic programming, right? A method for solving complex problems by breaking them down into many of the simpler sub problems. Faham kan? Okay, so this is what you learn in chapter 3, how to perform pairwise sequence alignment using matrices. Right? And the pairwise sequence alignment is the complex problem, and then you are going to solve. So in order to solve this complex problem, and then you have to divide them into many of the sub problems, which are meaning that every single cell in a matrix you can consider as a sub problems. After you combining all the sub problems, and then you can solve the complex problem. This is example of the dynamic programming. The aim of the dynamic programming is to maximize the sum of the alignment score for each pair of the sequences. So you see which of the alignment score give you the bigger value, and then you track back, and then you get the pairwise sequence alignment, right? This exact method can generate optimal global alignments, but these exact methods are very time consuming, especially dealing with many of the sequences, especially when the sequences that you are going to align are very long. All right. This exact method is only feasible for short sequences, only feasible for a few of the short sequences. If you let's say if you would like to align 10 sequences with 10 amino acids, the matrix here no longer in 2 dimensions. If it's spanned in 10 dimensions, if involve 10 sequences, this matrix will span in 10 dimensions. So, and then if they span in 10 dimensions, and then each of the sequence they consist of 10 amino acids, you have to solve many of the sub problems in order for you to get the alignment. So it's very time consuming. So if it involves 10 sequences with 10 amino acids, so how many of the cell matrices you are going to solve? 10 times 10 for 10 times. So meaning that you have to solve 1 power of 10 sub problems in order to get 1 multiple sequence alignments consists of 10 sequences and 10 amino acids. So only 10 amino acids and 10 sequences, you have to solve these big problems. And then majority of the protein sequences is not 10. Majority of them is more than 400 amino acids, or about 400 amino acids. Most of the protein sequences is about 400 amino acids. Okay. How do you overcome the limitation of the exact method? Do you know what is the limitation of exact method? Limitation dia apa? The exact method limitation is
Time consuming.
Cannot
use long sequences.
Okay, time consuming. So how do you solve this problem, this time consuming problem? The opposite form of the exact method is non-exact method. Using non-exact method to solve the time consuming problem, right? And then this non-exact method use heuristic approach. Do you know what's a heuristic approach?
No, doctor.
This non-exact method is feasible in time, right? Because they have the way to do that, and because this non-exact method, they use heuristic approach to solve to conduct the multiple sequence alignment. For example, here is progressive alignments, right? But this heuristic approach, which refers to experience-based approach, ecological, the past experience the scientist has discovered, right? This non-exact method using heuristic approach with the experience-based technique. This method does not guarantee to produce optimal alignments. Okay, just now non-exact method, and just now the exact method can produce optimal alignment, right? But it's very time consuming. And then this non-exact method cannot guarantee you the optimal alignments, but they can guarantee you will obtain one of the good alignments. There are many of the good alignments. Maybe it could be to align sequences with 100 MSA, 10 sequences with 100 MSA. Maybe there are 10 good alignments. All right, and then this non-exact method, they will guarantee you to obtain one of the good alignments, but may not be the optimal alignment. Faham tak? They compromise a bit, dia mungkin the accuracy lah, but it's more faster. They not guarantee you for the best alignments. Right? The progressive alignments, they compute pairwise alignments for all the sequences. Right? They compute pairwise alignment for all the sequences. Right? For example, if there are 5 sequences, sequence 1, 2, 3, 4, and then they will align sequence 1 with sequence 2, and then sequence 1 with sequence 3, sequence 1 with sequence 4, sequence 1 with sequence 5, and then 2 to 3, 2 to 4, 2 to 5, and then 3 to 4, 3 to 5, all the pairwise yang they will have to compute the pairwise alignment for every sequences, and they are going to perform the multiple sequence alignment, and then it begins the alignment with 2 closest pair. Right? The 2 closest pair, meaning that this pair will share the highest identity among all the sequences here, and then they will align first. After they align the most closest sequences, and then they will add on the next closest sequences. Okay, meaning that they can add on the 3rd or the 4th sequences into the existing alignments until all the sequences adding into the alignments step by step, but begin with the most closest 2 sequences and then add on the next closest sequences when you do it. So that's why we call this as progressive alignments. Right? They produce alignments step by step, progressively, add in sikit sampai habis. Okay, this is an example of the progressive alignments, right? Okay, this slide summarizes the step of the progressive alignments. And then you see, in order to align how many sequences here? 4 sequences here, and then you have to compute the pairwise identity for different pair. Right? You have to compute this table. Right? From this table, this is, you see, I write here. This is distance matrix. If distance matrix meaning that the smaller the value, the closest the sequences, right? Because because this is a distance matrix, it's not the identity, right? Or it's not the similarity matrix. If I write here similarity matrix, meaning the bigger the value, the closest the sequences, right? But this is distance matrix. The closest or the smaller the value, the closer the sequences. So you see from the value in this table, sequence number 2 and number 4, only 1. And then sequence 1 and 3, 2. So and then the rest 5, 7, and 11. Meaning that the distance between sequence 2 and sequence 4 is the closest. All right. So just now, I summarized the picture of the progressive alignments. They will align the closest pair of the sequences first, right? So in this case, which of the pair of the sequences will align first? Which pair will align first?
Sequence 2 and 4.
2 and 4.
Okay, 2, 4, first, right? So the closest sequences S2 and S4 align first, followed by the next similar pair of the sequences, which is S1 and S3. And then the gaps are added to align them. Okay, this is how. Okay, in order to align 4 sequences using this formula, you have to compute the pairwise distance matrix for how many of them? 1, 2, 3, 4, 5, 6. 4 minus 1 equal to 3, and then this is 4. 3 times 4 divided by 2, so it's 6. You have to perform 6 pairwise alignment to get the distance score. Right? Okay, and then the multiple sequence line following the tree from the A. This is the guide tree. Right, the guide tree depending on the distance metric they obtain from here. So since the two most closest sequences here is S2 and S4, and then they will align S2 and S4 first. And then during the alignments, they will place a gap to get to optimize the alignments so that we can get the purpose of the progressive alignment is to calculate the sum of pair score. Right, so they will place the gap here so that the sum of pair score for these two sequences will be the biggest. All right, so place a gap to maximize the alignment. Okay, S1. Okay, and then align next most closest sequences, which is S1 and S3 into these existing alignments. Okay, you see the aligned sequences, they follow the guide tree near sequence order, S2, S4, 1, and 3. 2, 4, 1, 3. So please take note. These are the gaps introduced into the most closest sequences during the early alignment. The first pair here, the gap will remain the same throughout the alignments, even though you add in the next closest sequences into the alignments. Right? You see, after you add in sequence 1 and sequence 3, and the gap here will remain the same. Tak boleh ubah lah. This 3. Right? The existing gap will remain the same, but they can add in another gap, which is not the existing one, to get better alignments in the context of as a whole, right? So the limitation for these alignments is once a gap, always a gap, right? Once the gap introduced in, the gap will remain the same throughout the alignments. Once a gap, always a gap. This is the limitation for progressive alignments. Okay, I give you one example here. Okay, even though the progressive alignment is faster than exact method, there is a limitation, which is once a gap, always a gap. The gap is added to terminal end to align cat and fat. Okay, we align these two sequences first. Graph here the first cat and graph here the last fat cat. And you align. Okay, you see the cat here can align with the fat, and the cat here can also align with the cat. And then why the progressive alignment prefer to place the gap at the terminal, not in between here? Kenapa? Why not the cat align with cat and then give the gap for fat? Huh? What? Yes, because no penalty or no cost for a gap at terminal end. Okay, this is the limitation. The gap is added to terminal end to align the cat and also the fat, because no cost penalty for the gap placed at the terminal end. So if the gap is placed at this color fat, and then they will cost some penalty. And then if the gap is at terminal end, no penalty. If no penalty, meaning that the sum of pair score will be higher, right? So they will prefer to place a gap at the terminal end. Even though they may not the best alignment, huh? Because this just considered only considered only in the context of the two sequences. Okay, the problem exists when the third sequence is aligned. So the third sequence, when the third sequence is aligned, it turns out that the two cats, the initial two cats in the initial alignment should align at the same column to get better score. So after the third sequences added into the alignment, right? And then they found that the cat at the initial alignment, they should align at the same column. But the error has been introduced in at the early alignment, and it will remain the same, right? Because of the limitation for the progressive alignment is once a gap, always a gap. This is a limitation, right? So regardless, after we add the third sequences into the alignment, they found that, oh, this is not the right alignment, but we have introduced in this before, and then the gap has to be remain the same. Right. That's why when adding the third sequences here, graph the very fast cat, even though they found that the cat is misaligned here, but the error has to be continued. This is the limitation of the progressive alignments. Okay. But at the final alignment, the misaligned cat remain in the alignment after all the sequences added in, and then confirm this cat should align at the same column in order to get a better alignment, but the error remain there because of the limitation of the progressive alignments. Once a gap, always a gap. Okay. The progressive alignments, they trusted more the placement of the gap in initial alignments. Do you know why? Why they trusted more the gap introduced into the initial alignments and not trusted the gap introduced at the subsequent alignments? Kenapa? Ecologic. Why?
Two most closely related sequence.
What?
Because this is the two most closely related sequence.
Okay, because the initial alignments, remember just now how the progressive alignment is constructed. They will align the two most closest sequences first, meaning that this is the most closest sequences. They trusted more the gap introduced into the most closest sequences. All right. So since the identity share between this pair is the highest, so they believe that the gap that interest at early alignments is the right one. All right. Okay. How does cluster W improve its ability to generate multiple sequence alignments? How cluster W improve its ability to generate multiple sequence alignment? Just now you have learned about a no cost at terminal, no cost place at the terminal end, right? This is one of the feature of the cluster W. There are a few more. Siapa dah baca note? Are you sure you have watched the video or read the lecture note? Okay, in one of the slides in my lecture note, these are the example that I use for the lecture note taken from the journal. Right? Okay. The sensitivity of cluster W for aligning divergent protein sequences has been improved by this feature of the cluster W here. Right. The cluster W, they downweight near duplicate sequences and they outweight the most divergent sequences. Right. Meaning that they give the smaller value for duplicate sequences. Right. For example, here, the smallest values here is 0.13. So the HBA host and also the 1, 2, and align with HBA human. Okay, this 0.13 is the lowest weight. They downweight near duplicate sequences because when align two sequences, if high identity, meaning that is many of the information is duplicated. So they will provide a smaller weight for duplicate sequences, and then they outweigh for the more divergent sequences. Which one is the most divergent sequences is 0.77 between myoglobin for the well and also the align with lemur. One, two, and host one, this one, and also this one is the more divergent sequences in this example, right? So this is the first point or the first picture of the cluster W. How they make use of these to get the alignments. Okay, the second one is the different scoring metrics for different alignments. They employ different scoring metrics for different alignments. For example, if they align two sequences that share the identity in between 80 to 100% identity, they will use PAM20 metrics for the alignments. If a pair of sequences share about less than 40% identity, they will use PAM350 to perform the alignments. So they use different scoring metrics for different alignments. And then the third, residual specific gap penalty. They employ residual specific gap penalty, meaning that the gap penalties are not the same throughout the alignments. Okay, how they do that? They assign lower gap penalty in the loop. So this is the loop. They assign lower gap penalty, and then they give higher gap penalty at the amino acid that form secondary structure. For example, this is a beta conformation and alpha helix. Okay. We know that regardless the how high the identity of the protein members of protein in a protein family, either they share 20% identity, or they share 40% or 80% identity. When we perform multiple sequence alignment, you will notice that the secondary structure normally will align at the same column. And then regardless how high the identity of the proteins, the most conserved region are the secondary, is the region of acid that forms secondary structure. And then the most variable region is the loop that connecting secondary structure, right? Because a loop is highly variable, right? And then this cluster W, they give a smaller gap penalty if you like to introduce in the gap into this loop. So like they have a lower penalty. If you like to place a gap into the secondary structure, higher gap penalty. All right. This is because the secondary structure is more conserved regardless of how high the identity of the proteins. Proteins normally conserve in the area of the MSA that form the secondary structure. Proteins are normally less conserved, or proteins are variable in this loop region. The loop region, normally they are exposed outside, interact with the water, and then the secondary structure, they will pack into the core or center of the proteins, right? And then this secondary structure is normally conserved regardless how high the identity of the proteins. Okay, and then the fourth feature of the cluster W, they reduce gap penalty for gap extensions. For example, this example here, okay. Okay, for this one, this is not the best example. Just now, yeah, the terminal end gap, because of no cost, and then they will place the alignment gap at the terminal end because of reduced gap penalties mean that, okay, this is the gap opening, and then this one, the second one, is the gap extension. The reduced gap penalty meaning that the gap extension with less penalty. Normally, when you check on the parameters for to perform multiple sequence alignment for cluster W, normally the first gap they introduced tends to have higher score, and then the additional gap introduced in the same gap will have a smaller score, okay? And then the fifth feature of the cluster W is equal initial gap opening and extension penalty throughout the sequence element. Regardless the gap introduced into here or the gap introduced into here, they will use the same gap penalty. Penalty to introduce a gap, and then penalty to extend the gap will be the same regardless the position of the gap in the alignments. And then no cost at terminal gaps. For example, this S1 and S2, okay, the gap will be placed at the terminal end because of no cost penalty. If they place the gap at the terminal end, they tend to have higher sum of pairs score as compared to if they place a gap in between. So that's why when the gap placed at terminal end, the cluster W is prefer this type of the gap because of the no cost at terminal end. Okay, what are the pros and cons for progressive alignments? Okay, just now the exact method, the cons is time consuming. The pro is optimal alignment. And then the progressive alignments, they can overcome the limitation of exact method, which is time consuming. The progressive methods can perform better than exact method. so they can overcome. The pro is they can overcome the limitation of exact method, which is time consuming. And then the cons for the progressive alignment is just now the alignments. Once the gap is introduced at initial alignment, they will remain the same throughout the alignment, because once a gap, always a gap, right? So the limitation for the progressive alignment is once a gap, always a gap. And then the pro is they overcome the limitation of exact method, which is time consuming, by providing one of the good alignments, right? But these good alignments may not be the best alignments, right? And then the limitation is once a gap, always a gap. Okay, and then for the exact method, it's not feasible for the alignment of long and many sequences, okay? And then it's because of time consuming. So the progressive alignments can overcome the limitation of the exact method, can align long sequences, but the limitation is once a gap, always a gap. And how do you overcome the limitation of progressive alignments? Siapa boleh jawab? How do you overcome the limitation of progressive alignments? What is the limitation of progressive alignments?
Gap.
Once a gap, always a gap. And then how do you overcome this?
By using exact method.
No, the progressive alignments overcome the limitation of exact method, and then, but the progressive alignments, they have the limitation once a gap, always a gap. Meaning that once a gap introduced at the initial alignments, which is with the highest identity, the gap will remain the same throughout the alignments. And then how do you overcome this gap? Meaning that a solution that can adjust the gap that placed at initial alignments. Betul ke dah baca ni?
Iterative approach.
Yeah, iterative approach. And then how iterative approach overcome the limitation of the progressive alignments?
Profile
Do-
alignment.
Do refinement of the sequence.
Yeah, yes, they define the alignments using the method profile alignments. They will cut the tree into two and then create the profile A and then profile B, and then they align two profiles to get a better alignment. And then meaning that the initial gap introduced in the alignments will be adjusted because they will create the profile A and profile B again, and then realign the profile to get a better alignment. Right? So the iterative method, they compute a suboptimal solution using a progressive alignment strategy. Okay. Even though the iterative approach, they can overcome the limitation of the progressive alignment, but they're still using the progressive alignment strategy. But they keep on modifying the alignments using the dynamic programming or other methods until a solution converges. They will keep on modifying the alignment until no more improvement in the alignment is obtained after that, and then they will stop, right? Meaning that it will repeatedly modify the alignments until no improvement on the alignments. The iterative approach, they create an initial alignment and then they modify it to try to improve it, right? And progressive alignment methods have the inherent limitation, meaning which is once a gap, always a gap. Once an error is generated in the alignments, it cannot be corrected. And then the iterative approach can overcome this limitation by employing profile alignments. Right? They will chop the guide tree into two and then create the profile A, meaning that they recreate profile A and then profile B, and then realign profile A with profile B to get a better alignment. So you see, even though the iterative approach can overcome the limitation of the progressive alignments, but the iterative approach still using progressive alignment. Don't confuse, right? Tahu tak? Meaning that the iterative approach, they combine the method of progressive alignments together with profile alignments. They improve it by using profile alignment to get a better alignment. So not only the progressive alignments is use the progressive alignments to do the alignments, the iterative approach also use the progressive alignment to do the alignments, but with additional feature, which is profile alignment. How they modify the alignments by using this dynamic programming to get the best sum pair score until the solution converge. For example, of the iterative approach, for the example of the program that use iterative approach is master. In the next chapter, I think chapter 7, phylogenetic tree, you will learn about one software because it's Mega. This software can use to construct a phylogenetic tree, and then one of the program that used to align to perform the multiple sequence alignment in the Mega is master, and then the second one is cluster. Master is more accurate than cluster W, but master is faster than cluster W. So now clear, right? The iterative approach make use of profile alignments to improve the multiple sequence alignments. Right? They realign the profile to get a better alignment. Okay, I just described here one of the methods, the most popular one, which is master. Okay, the master consists of 3 steps: build, improve, and refine. So the step 1 is build a draft progressive alignment. Right? The master use camel counting to compute distance matrix. So the camel counting here, meaning that no alignment is performed. Right? They will divide the sequence into a defined word. For example, during the blast P, how the blast P perform the blast, they divide the sequence into 3 words, right? 3, but these 3 words are overlap, right? Kan? Ingat tak? Blast P.
Ingat, Doktor.
Clark? Yeah. Blast P, they divide sequences into 3 words. Same as the master, the camel counting here. They divide the sequence into 3 words, 3 MSA, but these MSA are overlap, right? You know, 3 words, right? And they do not perform the pairwise sequence alignment to compute the distance matrix. Instead, they use the camel counting to compute distance matrix. Right? And then the master use ACMA and neighbor joining method, which is NJ, to construct rooted tree. And this is rooted tree is a guide tree. The guide tree, right? To see the order of the sequences to be aligned in multiple sequence alignments, right? The progressive alignment one is constructed follow the order in the guide tree. This is unrooted, and then they will place a node in maybe here in order to convert unrooted into rooted tree, and then to get something like this, and then to see the sequence of the order of the protein sequences here in order to appear in the alignments. Right. Okay, this is how distance matrix is performed using camel counting. The camel counting does not perform full alignments. Instead, the camel counting, they divide the sequence into a defined word to calculate the distance. For example, the sequence ATG, TG, TG, the camel counting, they divide this sequence into ATG, and then TGT, GTG, TGT, GTG. So from this short sequence, you have 1, 2, 3, 4, 5 words derived from this sequence. Same thing for the other sequence, CAT, GTG. The first three words CAT followed by ATG, TGT, GTG. So for this short sequence, you will 4 words are derived from this short sequence. So, and then they see what are the consensus in this the word formed by these two sequences. So consensus here is not a consensus. The type of the word that appear in the two groups. So CAT only one, okay, and then ATG, yeah, and then TGT is mother, and then GTG. So from this pool of the 3 words, and then there are 4 types. So they list on the 4 types here, and then they count how many times they occur in the pool of the word derived from this sequence. For example, CAT from this pool, tak ada kan? 0. And then ATG only 1. And then TGT appear twice, so it's 2. And then GTG twice. Same thing as here. And then they use this formula to calculate the distance. This is how the camel counting compute the distance using this method for the muscle alignment. Okay, the second step, improve the progressive alignments. The muscle computes pairwise identity from multiple sequence alignments. 1. Okay, just now we obtained the rough multiple sequence alignment, the first version of multiple sequence alignments, and then from this multiple sequence alignment, the muscle calculate the pairwise identity between sequences based on the context of the multiple sequence alignment here. Okay, and then the muscle construct new guide tree using Kimura distance matrix. They form the new guide tree using Kimura distance matrix, where it only take into account exact match. Right, maksudnya kalau if the sequences they align identical IMSX align together at the same column, and then they will count. All right. Okay, this is one, and then they also will and then for the Kimura method, they employ the same penalty for all of the amino acid substitutions. Right? If they are amino acids substituted, and then they will minus the same penalty, meaning regardless the substitution for alanine to leucine or alanine to lysine, even the substitution from one group of the amino acid to the other group of amino acid, or substituted from in the same group of amino acid, they will use the same penalty for all of the analysis substitution. So the Chimera distance metric here, they use two approaches to plot the guide tree to get the score to plot the guide tree. One is they only count the exact match, and then the second one, if there is a substitution, they will employ the same penalty regardless what substitution in the alignments. And then finally, the master will iteratively compare and improve the new and the old tree until no improvement. They will compare the new and old tree and until no improvement, and then you get until no changes in terms of the tree. Okay, and then the last step is they will refine the multiple sequence alignments. How they refine the multiple sequence alignments? Just how the progressive alignments. Once a gap, always a gap, right? Once a gap is introduced into the closest pair of the sequence, the gap will remain throughout the alignments. And then in order to rectify, in order to correct the misalignments introduced in the initial alignments, and then how the marshal refine the alignments is they split the tree into two. Right, this is the tree just now here. They cut tengah-tengah into two, and then they make profile for this half and then this half. There are two profiles from here and from here. All right, and then they realign the profile. Okay, they split the tree into two and perform the profile alignments, right, until the solution are converged with no improvement in the sum of pair score. Right, if no improvement further, and then the multiple sequence alignment that obtained is the final alignments. If there is improvement, they will keep on repeating this iteratively. That's why they call it iterative approach, because meaning that they were repeating this cycle again and again until no improvement further. Right? So what are the pros and cons for iterative approach? So apa limitation dia? Ada the limitation for the iterative approach, or a pro is they can overcome the limitation of progressive alignments, and the iterative approach can overcome the limitation of progressive approach, which is what is the limitation of what's a gap, always a gap, and then the iterative approach can overcome the limitation of the progressive alignments. Once a gap, always a gap. Right? And then the limitation is do not use information about the multiple sequence alignment to guide the final alignment. So they just take into account the alignment between pair of the sequences to calculate the alignment and also to calculate the identity. They do not make use of the information with other sequences to improve the alignments. How the iterative approach overcome the limitation of the progressive alignments? By performing profile alignments. Right? Okay, please take note. This iterative approach, they combine the progressive alignment plus additional feature, which is profile alignment. So there are two things. Okay, although the iterative approach is not grouped under the progressive alignment, but they still use the progressive alignment with additional feature, which is profile alignments. They combine the two progressive alignment and profile alignments. They combine them together and then into to make another new method, and then they call it as iterative approach, because they iteratively improve the alignments but cut the tree into half, and then profile it, reprofile the alignments, and then align together until the solution converge, until they will repeat iteratively again and again until no more improvement. That's why they call it iterative approach. Even though they group under iterative approach, they are still using progressive alignments to get the sum of pair. Progressive alignments meaning they add in the align the sequence start from the two most closest sequences first, and then adding in the next closest sequences until every sequences finish. The consistency-based approach offers better accuracy than iterative approach. The consistency approach adopt a different approach by using information about multiple sequence alignments to generate or to guide the pairwise alignments. So just now I told you the iterative approach, the limitation is does not take into account the relationship with other sequences to guide the pairwise alignment, right? But this consistency approach, they try to overcome the limitation of the iterative approach by taking information from by using the information from multiple sequence alignments to generate and to guide the pairwise alignments. And then the consistency-based approach use database of both local high-scoring alignments and also the global alignments to create the final alignments. Right? They use two types of the alignments. One is local. No, it is a short alignments, and also the global, the whole alignments of the sequences. They combine together to improve the alignments. Okay, how the consistency approach make use of the information from other sequences to guide the alignments. The idea for the consistency is that for sequences X, Y, and Z, if residues Xi align with Zi and the Zi align with Yi, then the Xi should align with Yi. So they would like to align sequence X with sequence Z. But in some cases, when you align the sequence X and sequence Z together, you may not be able to get the best alignments, because especially if the identity shared between sequence X and sequence Z is very high. So they make use of another sequence with sequence Y here. They align X and Y first, and then Y and Z. So, and then they align together X, Y, Z using the context of the Y to align sequence X and Z. Right? So they make use of the multiple sequence alignments information to guide the alignments of the X and Z. This is the feature of the consistency-based approach. They make use of the information from multiple sequence alignment to create the pairwise alignments. That's why from my lecture slide I uploaded to Putra Blast, you see many of the multiple sequence alignments for the distantly related globin members, family members. The progressive alignment cluster W, and then the muscle, they are not able to align the catalytic residues histidine, right? But the consistency-based approach is able to align the catalytic residues histidine at the same column, right? That could be because of they make use of the information from multiple sequence alignment to create the pairwise alignments, right? So that the alignments that they obtain is more accurate as compared to the rest of the method, right? That's why they from the multiple sequence alignment generated using a consistency-based approach is able to align the catalytic residues histidine at the same column. Okay, and then I just explain one of the a famous program is TCOFI under the consistency-based approach. Right. This is the layout for TCOFI strategy. Right. The TCOFI use cluster W to perform global alignments. And then the TCOFI they use L align for local alignments to find multiple matching subsegments in two sequences. Okay, and then all of these global alignments, right, and also the 10 of the local alignments are combined to construct the primary library, right? And then the extended library is constructed by recalculating the weight through other sequences. So the example is in this slide how they are derived, right? Okay, A is the 4 sequences are aligned using progressive alignments, cluster W. You see, example given just now, the cat here is misaligned using progressive alignments. It's because the gaps introduced into the most closer sequences at initial alignments, the cluster W assume that this is the right gap introduced in. And then unfortunately, at initial alignment just involve 2 sequences. There could be error. And then when subsequent sequences are added in, and they found that the cat is misaligned. But the limitation is the progressive alignment is once a gap, always a gap. And then they are not able to rectify the error at subsequent alignments. So this is the error introduced in the cluster W. They misalign cat. Okay. And then the step B here, they compute global and local alignment, and then they will convert the weight will assign to each of the pairwise alignments according to the sequence identity that they obtain. Right. For this field one, the identity is 100% because they align totally, right? And then this one, 88%, 8, 11, 4, until here is 14, 15, 16. 16 identical divide by 21. So you get 88. So this weight is actually a percent derived from the identity of the alignment. And then C here, the weight are recalculated through the relationship with other sequences to generate the extended library. So one of the features of the consistency-based approach is to make use of the information in the multiple sequence element, or to make use of relationship with other sequences to compute the pairwise sequence. So from here, the weight are recalculated through a relationship with other sequences for that in order to align A and B, and then they align A and B through the relationship with C, and align A and B through the relationship with D. So from here, you see they calculate the weight for each, the new weight for each of the alignments, get 88, 77, and 100%. And then from this information, and then they combine all of the alignment here into one. Okay, if all of the pair here align at the same column, basically THE for this pair, and THE for this pair, and this three, and then THE for this three. So all are the same color. So the way you will see the linker between the THE here is more intense, because the more intense the linker here, meaning that they align at the same column. And then for this graph here, only these two pairs, so you see less intense. Okay, and then the cat as well here, and then the fat, right? So from here, they will readjust the alignments using the progressive alignment, and then this is the final alignment that you will get. Graph here, the last, the fat here align with the fast, and the cat with the cat. So you see, initially the A and B, they misalign the cat, right? Now, using the information relationship with other sequences, and then they can rectify the error, align cat with the cat. You see, the cat here align with the cat, and then initially this one, the fat align with cat, right? So fat align with the cat, the line is thinner, right? Fat align with the cat is thinner, and then the cat align with the cat is thicker. So the correct one is will be cat align with the cat, and then FAT here, FAT align with FAST is thicker as compared to the last align with the fast is thinner. So the final alignment will be FA get T align with FAST, right? Macam tu. And then the last here ini kosong, so there's a gap in here. So this is the final alignment. This is how the consistency-based approach rectify the error generated in the initial alignment by taking into account the information in the multiple sequence alignment to guide the creation of the pairwise sequence alignments. So this is the advantage for these methods. No wonder the consistency-based approach is able to align the characteristics histidine at the same column. Right? So what are the pros and cons for consistency-based approach? Just now, the pro for consistency-based approach is what? Class, you're just on the video and then stay away. Right? Nobody answer my question.
The pro is using the MSA to guide the pairwise alignment.
Okay, and then the limitation?
It does not take consideration about the structural information.
Okay, correct. Okay, the pro is the consistency approach. They employ iterative approach and progressive alignments with additional improvement by take into account the information of multiple sequence alignment to guide the pairwise alignment. So they still use the progressive alignments and still use the iterative approach for the alignments, and then with additional feature, which is information of multiple sequence alignment to guide the pairwise alignments. The limitation is the consistency-based approach does not take into account structural information for multiple sequence alignments. Please remember, many of the protein sequences, they share low sequence identity despite having similar structure. For example, just now, myoglobin and a subunit of the hemoglobin, they have similar structure, but the identity share between them is just 25%. There are many of the protein in this world are like this. Right? So if we take into account the structural information, in some cases, we may able to improve the alignment because we take into account the alignment at the structure context. So this is structure-based method. Okay, a protein is more conserved than DNA sequence because of degeneracy of genetic code, in which substitution at DNA level, which is the codon level, may not change the identity of the protein sequence because of degeneracy of the genetic code. And then the structure is more conserved than protein sequence because of conservation substitution, meaning that substituting of MSA from the same group of the MSA. For example, alanine, leucine, isoleucine, they are grouped under aliphatic non-polar amino acids. So substituting of the alanine to leucine or isoleucine, they will still group under the same of the MSA. We call this as conservation substitution or conservative substitution. This type of substitution normally do not change the structure of the protein. Because you guys ambil the protein engineering, if you take the protein engineering, you will learn all this in detail. And then as the structure evolves more slowly, and then protein with limited sequence identity can have similar structure. Okay. One can make use of the structure information to guide the multiple sequence alignments. For example, the espresso use tertiary structure to guide the alignments. This is myoglobin, this hemoglobin. The structure are the same, but the sequence are very, very different. You see from these two sequences, this is myoglobin, and this is subunit alpha chain of the hemoglobin. So a lot of variation at the sequence level, but highly similar at structural level. Okay. This is the flow for the espresso. The espresso, they automatically find the right template structure with identity more than 60% and coverage more than 70% to be used as a template to guide the alignments. Let's say if you would like to align two proteins, okay, every single protein sequence will be blasted against protein database to check is there any template structure with more than 60% identity, and then they cover at least 70% of the sequence. For this sequence and also this sequence, they will blast individually to the database to get the representative template to guide the alignments. Once every sequence with structural homolog has been assigned its template, and then the template are then aligned using structural aligner. We will align the structure for template A and structure for template B, and then they get this the structure template alignment, and then this structure-based alignments are used as a template to realigning the original sequences. Okay, after align the structure template alignment here, perform structure template alignment here, and then our sources sequences will be added into the alignments, because initially we use this sequence to blast against database, and then we already have the alignments between our sequence and also the alignment with and the alignment with and the sequence from the database. We align all this together, right? And then the template sequences are then removed away, and then finally we get the sequence alignments for our sources sequences, right? Okay, to summarize the 5 approach to multiple sequence alignments. Okay, the first method that I introduced today is the exact method. Okay, this exact method using dynamic programming. to get the sum of pair score, right? And then the pro for the SI method is optimal alignments, and then the con is time consuming, right? And then in order to overcome the limitation of the exact method, which is time consuming, and then the progressive alignment is introduced. The progressive alignment is able to overcome the limitation of the exact method, which is time consuming. And then this progressive alignment is able to produce one of the good alignments, but may not be the best alignments. For example, here, the Fern-Doolittle approach and Castellari, they use the progressive alignments. And then the limitation for progressive alignment is once a gap, always a gap. Right. So this is the limitation. So in order to overcome the limitation of the progressive alignments, the iterative approach is introduced. The iterative approach makes use of progressive alignment and also the dynamic program, because the dynamic programming here is to get the sum of pair score, to calculate the sum of pair score. Right. And then the pro is this iterative approach can overcome the limitation of the progressive alignment, which is once a gap, always a gap. How? Using profile alignments. And then the limitation is this iterative approach do not use information about the multiple sequence alignment to guide the pairwise alignments. Right. So how are we going to overcome the limitation of this iterative approach? By make use of consistency approach. The consistency-based approach, they combine the method of progressive alignment and also iterative approach with additional feature, which is make use of information of the multiple sequence alignment to guide pairwise alignments. Right. So by introducing this information in, and then they can improve further the accuracy of the multiple sequence alignment. But the limitation is this does not take into account structural information, especially when the sequence identity is very, very low. So the last approach is using structure-based method. Use the structural information to guide the alignments. Okay, you can see how good this method is, because this method is normally used for benchmarking study. For example, in the Bali base, they make use of the structural information to produce a data set for scientists to perform the multiple sequence alignment, and then for scientists to develop multiple sequence alignment algorithm. And the limitation is not every single protein sequence have the template in the protein data bank. Okay, that's all for my today's lecture. Any question?
Doktor, I have a question. Untuk structure-based method, memang semua the sequence that is selected have to have the PDB file untuk dapatkan, untuk go through the structure ke, nak dapatkan the 3D structure alignment?
Yes, they have to search against the protein data bank in order to get the template to guide the alignment. Right, and then the template has to be at least 60%, and then with 70% coverage. That's why the limitation here, not every protein has the profile here, a PDF file. I think this is the limitation.
Is that why kita orang tak dapat like the structure based? Doktor?
Mungkin,
What tu?
yeah, if no structure, it may not be able to give you the right alignments. But now, because of the structural genomic project, now the scientists have sequenced many of the microorganisms, and then the genome of the microorganism, and then they have annotated, they have predicted the structure for every single protein in the genome. And then sampai sekarang you see the new fold, almost new fold has been discovered now already, because majority of the protein structure has been solved either using X-ray crystallography, MR, or using in silico structure prediction method. And then because of structural genomic project, and then many of the new structure has been deposited into the protein data bank. And then this can serve as a template to guide the alignments for almost all of the sequences that are available today.
Okay, thank you, Doctor.
Okay, and then next week, I will teach you on how to find a novel gene using NCBI BLAST. In order to find a novel gene, you have to combine a few of the NCBI BLAST that you learn from Dr. Nurifiza in chapter 4, I think. T plus M plus plus X plus P plus N, combine this together in order to find the novel gene and also to validate the novel gene. And then how to find the novel gene, and then they are the skill, and then we have to take into account to see the E value as well. Cannot be near to 0, which is significant. For sure, you will not get the novel gene, and then cannot be too high. To have to take the balance. I will give you. I will show you the strategy next week. Next week will be my last lecture with you guys, and then I will post. I will upload my last assignment to Putra Blast next Tuesday after the lecture, right? And then in order to help you to understand the lecture better, I will keep on posting in the question to Putra Blast in the forum. So please participate in the forum. This can help you to answer the exam question later on. And then next, would you like to have the second test on next week or week 11? Second test. Class?
Week 11.
11. Doctor.
Okay, you prefer the normal second test or simplified of second test?
What's the different, Doctor?
What? Different?
Apa maksud?
Oh, the normal second test is like some in the bilik kuliah, and then face to face, the detail one with two versions bahasa English, bahasa Melayu tu, and the simplified one can be in the form of the quiz structure or short answer macam tu lah. Nak mana satu? Number one.
Simplified.
Simplified one.
Simplified. Okay, I try to prepare objective. Okay, fill in the blank.
Okay, Doctor.
Okay, Doctor. Objective.
Objective. Okay, because of the objective and then simplified version, and then the time given cannot be too long because I know that there are many cases like the cheating during the test last semester. I hope this will not happen in my class. Kita kena jujur masa jawab soalan tu. But I guarantee the question will not be difficult. Alright, and if you go through my lecture, face-to-face lecture in the form of the tutorial, I don't think if you understand, I don't think you will face any difficulty in answering the final exam question. Kalau you faham lah. That's why I posted the video for you to, and also the note for you to read first, and then have the tutorial section after that in the form of question and answer form, so that you know better when I ask this type of question, what are the answer that you expect to deliver lah, macam tu lah. Okay.
Okay,
Okay,
Doktor.
Doktor.
Okay, see you next week.
Okay, thank you, Doktor.
Thank you,
Okay.
Doktor.
Okay, bye.
Thank you, Doktor.
Okay.
Doktor.